All right, so this is May, June 2023, paper 5054, O-level physics. This is question number 1. He says this is the speed time graph of an object or of a car moving in a straight line. The first thing we need to always keep in mind is that the gradient of this graph will represent acceleration, and the area under the graph will represent the distance traveled by the object, right? So just a few pointers before starting the question. So in the first question, he says, describe the motion of the car as shown in the figure 1.1. Now, how do you describe the motion? You just have to talk about the graph in terms of how the object may be moving. So we can say that in the first section, the speed is constant. And to tell to the examiner, to show the examiner that how are we going to represent this, we need to understand that we need to talk about the time as well. So you will write down that for the first 10 seconds, or from time t0 to t10, the object was moving at a constant velocity as mentioned in the first statement. It is moving at a constant speed. And in the next section, we can say that from time t0 to t40 and beyond, let's say, it is moving at a decreasing speed, or you can say the speed reduces, but due to non-uniform deceleration. If it had been a uniform deceleration case, that would have been a straight line. It should have been a straight line. But if it's not, if it's a curved line, then this is a non-uniform deceleration case. And again, mentioning a timestamp that after 10 seconds, we see that from the graph. This further improves our impression in terms of the examiner, that we understand how to answer the question at least. In part B1, he says, at time t10, the engine of the car is switched off. Okay, fine. So there is no forward force on the engine or from the engine. The brakes are not applied. Okay, so the brakes are not involved. State two other forces that may act on the car. Two forces. Now, we understand that if the car is moving in the forward direction, there is a force from the engine or the driving force. And there could be three forces in the back if you apply the brakes. If you are not applying the brakes, then of course, friction from the tires and the drag due to the shape of the object trying to move through air. So we have to mention those two things, friction from the tires and drag due to air resistance. So these are the two forces that are going to stop the object from moving further or are going to try to produce deceleration. Suggest why figure 1.1 is a curve after t10. As mentioned earlier, over here, this is due to the non-uniform deceleration, but we need to identify why there is a non-uniform deceleration. You see, if we had to make an equation from Newton's second law, that equation would look like F equals to ma, and then the forward driving force minus all the frictional components equals to ma. Now we can see that the engine is not involved after the t10 second, and the brakes are not involved, but the drag and friction are. So the only equation we are left with is going to look like this: minus friction equals to ma, and we understand it is deceleration. So we don't have to really talk about the negative sign, or we don't have to think about it right now. So we can come to this conclusion, since mass is not changing, that friction or the drag or the friction components are proportional to the acceleration. We can see that the acceleration is not constant from the curve, which means that the frictional components would also be not constant. They would be changing. And we understand by this time that the drag or the air resistance depends on the speed of the object. Now, when the speed reduces, the drag on the object also reduces. So it's being negative, or you can say it is being reduced by a value that is decreasing with its own time. So for example, if previously the drag force was 50, producing an acceleration of, let's say, 2 meters per second square. Now, due to a reduction in speed, today, the drag may be at 35, which will proportionally produce a lesser acceleration, let's say 1.5 meter per second square. And as the drag reduces, the acceleration also reduces, which is evident from the graph as well, as the gradient previously is something else, and eventually the gradient has started to reduce. It has started to become less and less negative. So we explain this idea to the examiner as that the speed is decreasing. As the speed decreases, the drag also decreases, which causes ultimately for non-uniform deceleration to take place. And this non-uniform deceleration has caused the graph to be curved, right? Okay. In part C, we have the mass or time between t10 to 20. The speed of the car changes from 18 to 11. The mass of the car is 1200. Calculate the change in momentum. Now, for a change in momentum, we have the formula simply as the final momentum minus the initial momentum. So that would be mass into final velocity minus mass into initial velocity, which would be, if we want to take out the mass of the system common on the outside, that makes things easier. So 1200 will be on the outside, and then a simple change in velocity, which will be 11 minus 18, which will lead to a final answer of 8400 Newton seconds. Now, the negative sign only represents that it is undergoing a decrease in momentum in the reverse direction. Of course, momentum is a vector quantity. And since it is undergoing a deceleration, the momentum is changing backwards. So adding a negative sign or not is not going to be a problem over here. You can add a negative sign or you can leave it. It's your choice. So a change is 8400 and the unit will be Newton seconds, right? And calculate the average resultant force. Now, we've also done this topic from force in the momentum, that force is basically change in momentum divided by change in time. Now, change in time is fairly easy. From 10 seconds to 20 seconds, the change in time is nearly 10 seconds, right? It's easy to figure out. But the next idea is, where is the change in momentum? So we have already done the change in momentum in the previous part. We're just going to replace its value as 8400. So it comes down to 840 newtons of force. So this change in speed from 18 to 11 meter per second was brought by an average force of 840. Now notice he uses a word of average resultant force, not the resultant force, or he is using the word average because he understands that this is a non-uniform velocity. If the graph was a straight line with a uniform deceleration, then definitely this F, or the resultant force, would also have been a uniform force. But since it's not a constant value, it's changing. That's why he's saying that you can talk about this in terms of an average resultant force. That's why the word average is mentioned over here. These are little details we need to keep in mind. So question number 2, he says, state the energy stored in the battery. Now, in battery cells, fuel, like petrol or diesel or natural gas, and the food that you eat, the primary energy stored is the chemical potential energy in the bonds of the atoms. Describe in terms of the work done, the stage of energy transfer, or the stages of energy transfer. It's a very simple question, that from the battery to the kinetic energy scooter, how does that happen? So the battery has a chemical potential energy, which converts into electrical energy, or you can say the battery causes the electrons to move or pushes the electrons to move into the electric motor. The electric motor spins and now has mechanical energy. So it's primarily, in terms of the arrows that you've done in classes probably, it's chemical potential energy converted into kinetic energy of, sorry, not of motor, but first it will be converted into the electrical energy, and then it converts into the kinetic energy of motor, and then eventually kinetic energy of the boy or the scooter itself or the whole system, right? So the motor moves, this causes them to move forward, and hence the final state will be that one. So this causes the back wheel to move, eventually causes the scooter to have some kinetic energy, or it starts moving. Part B says the total mass of the scooter and the rider is 70 kg. The total kinetic, easy question. So the formula is half mv square. So 1/2 mass is 70 and the velocity right now is 4 meter per second as given by the examiner. So you don't forget to take a square of that. This comes out as 560 joules. So while the object is moving, it has 560 joules of energy. The next question is, the battery is marked energy capacity 0.35 kilowatt hours. Define what is meant by kilowatt hour. Now, whenever you encounter units in physics, you just have to put a value of 1 in their respective formulas. So kilowatt hour would mean you have to define 1 kilowatt hours. So if an appliance uses 1000 watts of power, again 1 kilowatts written as 1000 watts, in a time frame of 1 hour, then the energy consumed will be 1 kilowatt hour. So this actually stems from power equals to energy divided by time. Since kilowatt hour is a unit of energy, time goes over here. So this energy unit, that becomes power multiplied by time. So 1000 watts of power multiplied by 1 hour of time is actually equal to 1 kilowatt hours of energy. This is unit of energy. The next, he says the scooter stops working because the battery is totally flat. This means that there is no more energy stored in the battery. The battery has a recharge using a 70 watt power supply. Calculate the time taken for the battery to fully charge. No problem. So again, energy is equal to power multiplied by time. This is what we want to find out. So how much energy does the battery actually possess when it is fully charged? That is 0.35 kilowatt hours. So 0.35 kilowatt hours of energy equals to power. What is the available power that the battery can receive per second, or how much energy it can receive per second? So that is 70 watts. Now we have to convert this into kilowatts. So that will be 70 divided by 1000 multiplied by time. We have to make sure the units remain the same. And we understand that for this formula to be used, power has to be in kilowatts and time is found to be in hours. Now, when you do this, finally calculate, this comes out as 5. So we'll write down as 5.0 into significant figures, 5.0 hours. So if you plug in today, after 5 hours, this will be charged completely. Question number 3, he says a fixed mass of gas. When he says fixed mass, this means that there is no leakage and everything is airtight. Okay. Seal at one end and the column of mercury. Okay, mercury is free to move within the tube. There is no friction, no drag. The tube is slowly tilted to look like this. And he says not to scale so that you don't start taking measurement from the diagram. Don't put a ruler over here and start taking measurements. He's going to stop you from doing this. That's why I mentioned not to scale. The volume of the gas increases as temperature remains constant, which means that he does not want you to think about the temperature factor. He only wants you to compare the pressure and volume of the gas under these circumstances. So temperature is constant. It will not be discussed. It will not be thought about. First, he says, describe why the radiating that causes the pressure of the gas changes the pressure. Now, he's mentioning that pressure changes. He's not asking to justify whether the pressure increases or whether the pressure decreases. So you have to tell him that the pressure decreases, right? So mercury generates less pressure in the horizontal position. Why? Because over here, when it is in the vertical position, like this one, it has the help of the gravity. Due to gravity, it is exerting a pressure of rho GH on top of the gas. Now, when you do that, when you bring it to this horizontal position, you realize that according to the Earth's gravity, you're not exerting any more pressure right now. So whatever the gas pressure was on the outside, let's say, if this is the atmospheric pressure, the inside gas pressure is today equal because mercury is not participating in that scenario anymore. Okay, so the next idea is explained using ideas about particles. Now, whenever you encounter this question, you always have to think about atoms, right? Why the pressure of the gas decreases. Now, he says decreases when its volume increases. It's a general calling to this formula of Boyle's law. He wants you to discuss this formula. That is it, right? So as we understand that today, the volume has increased. So pressure would have decreased. Why would this happen? This is what we have to discuss. So you can say it's a fixed answer. If you want to memorize this, it's up to you. But the answer will remain the same. So higher volume, when we say higher volume, we're starting the question from this right-hand side, that if the volume is increasing or if the volume increases, what happens now? There are going to be less frequent collisions with the walls of container. If this is the container wall, the gas molecules are colliding with the wall and hence exerting a force. So the frequency of collision decreases, leading to reduced overall force on the walls due to a change in momentum. You see, force is responsible due to, or force comes due to change in momentum. Now, when there are going to be less atoms or particles hitting the surface or hitting the walls of container from the inside, ultimately the resultant force or the total force is going to get reduced because there are less particles. They're colliding less frequently because they're spending time in the motion or in the movement reaching up to the walls because now the room or the space has increased, right? So because of this change in momentum, so since the change in momentum has reduced, the force reduces. And since the reduced force causes less pressure, why? Because pressure is equal to force over area. We haven't changed the area, but we have reduced the force. Since the force reduces, the pressure also reduces. So it's a complete chain of thoughts that you should at least understand, or if you don't, then memorize the answer. This will be a part of other questions similar to this one. It says here in figure 3.1, the length of the column is 0.3. So this is figure 3.1, right? He says that the column is 0.3. How much is the pressure of the gas? Now he says calculate the pressure of the gas in the tube. So we understand that this is the gas pressure that is over here. Now, if the system is stationary, if the system is not moving, or you can say that the mercury column is stationary, it's not moving up, it's not moving down, which means that the system is now in equilibrium, which means that the pressure exerted by the gas on the upwards direction, because the mercury is trying to compress it, should be equal. So the pressure due to mercury, which is going to be rho GH because it's a liquid, and since it's an open tube, the pressure on the atmosphere, because of the atmosphere on top of the mercury, which is combined or which is being transmitted throughout the liquid up to the gas, these two components, atmospheric pressure and the pressure due to mercury, are being exerted on the gas. They are trying to compress it. but the gas is holding on its own. It's holding both of these two pressures or forces on its own alone. So we can say that the pressure of gas today is equal, because it is good enough to stop them from moving, is equal to the pressure of atmosphere plus the pressure of mercury, which is Hg, right? So the atmospheric pressure is given to us like this one into 10 raised to the power 5 plus rho gh, because mercury is a liquid. So this is going to be 14,000 into G, which is 9.8, into H, which is 0.3. Now, when you solve them separately, this is going to be 10 raised to the power 5 plus this will be 41,160. So in the marking scheme, he says that we need to see whether you've calculated this or not. It's okay, it's fine, as long as you've mentioned this one. So the final answer, the total pressure will come out as 141,160, which will be 1.4 into 10 raised to the power 5 pascals. So this is the pressure of gas which is trying to hold back. In part C, he says draw a graph of P and V, and again, this is what he's trying to ask you. The pressure is inversely proportional to volume, and he wants you to draw the graph. So now what he has done, he has given you one coordinate when the pressure is 1 and the volume is 1 unit as well. So 1 equals to 1 over 1 actually produces this coordinate, which is already given to you. Okay, fine. So we need at least 2 more coordinates to understand the full curve. Now you might have memorized this, or you might have memorized this graph like this, that this is an inverse proportionality graph like this one. But today he's asking you about the coordinates as well. So you have to coordinate, you have to put in these coordinates as well. Now let's see what those coordinates are. So he wants a coordinate at 2p and half p. So we understand that when you increase the pressure to 2p or twice the pressure, the volume has to decrease. So by this logic, we can see that if pressure is 2 times, and what will be the value of volume, right? So it will be halved. Volume will be halved. If you're increasing the pressure, volume will be halved. So we bring a coordinate over here at half v and 2 times p. Then we do the same thing for a new coordinate, which is over here. Now, when you decrease the pressure by half, or you reduce the pressure, let's say if this is p inverse, if you decrease the pressure, the volume increases by the same amount. So if you're decreasing the pressure by half or reducing it by half, the volume will double. So the new coordinate comes over here. Okay, so if you are unable to understand this, we can also go about this by another logic. You see, for a gas that follows, P is inversely proportional to volume. If you bring this over here, this becomes PV equals to a constant K, removing the proportionality, bringing in a constant. So no matter what variables you put for P and V, the answer should be a constant. So let's say that their multiplication produces an answer of 1. For the sake of example, if you have increased the pressure to 2p, if this is today 2p, then what should be the value of the volume? Again, this is 1. So when you bring this 2 over here, the volume V becomes 1 over 2, which is why we get this one, right? This coordinate. Similarly, if the product was still equal to 1 and you increase the, or you decrease the pressure by half, let's say you make this 1 over 2 P multiplied by what should be the V now, this will become equals to 2. That is how you get this coordinate, right? So you can either do this by algebra, or you can either do this by comparison method. You will get these coordinates nonetheless. Okay, so now let's move on to drawing the graph. So you just have to draw a straight line through these coordinates, right? Make sure that it's a freehand diagram like this. Okay, and please make sure that this also crosses the coordinate like this. It's difficult for me for this writing tablet, that's why. So you can use a lead pencil and draw it this way. It should look like something like this. It should be a smooth curve. Moving to the next question, he says that the atom particles are seen. It's a sample of iron. It's a solid, and a temperature is below its melting point, so it is still a solid. Now, in the first part, he's asking about the lowest scale. So we understand that Kelvin temperature is equal to degree centigrade plus 273, right? This is the equation that we already understood in the syllabus. He says, what's the lowest temperature on degree centigrade, Celsius, and Kelvin? We understand that Kelvin has a 0 Kelvin lowest minimum. Kelvin is not in a negative scale. It never is. So provided with this information, we can bring this degree centigrade plus 273 over here. So degree centigrade becomes equal to minus 273. So the lowest temperature on degree Celsius scale would be minus 273. On Kelvin scale, it will be 0. which is sometimes called as absolute zero. Similarly, we have the temperature of the solid increases, the sample remains a solid. Okay, you are heating it up. Describe how the motion of the particle changes. So when you heat up the particles, we understand from thermodynamics that temperature is proportional to the speed of the atoms, or in theory, it is actually the kinetic energy of the particle. Now, since the mass of the atoms is not changing, we conclude that this is actually the speed. So particles vibrate at a greater speed, as understood or memorized from kinetic model of matter, and with greater amplitude. They will be agitated and they will be vibrating. Let's say if they're vibrating at a smaller amplitude, at a high temperature, they will be vibrating at a greater amplitude. That is how it is different from a temperature when it is lower. The solid eventually melts or starts to melt. State what happens to the internal energy of the temperature solid. Now, the internal energy is actually dependent on the potential energy and the kinetic energy, right? Now, when it is melting, the temperature does not change. We understand that this is a change of state. That's why we call this a melting point, because it happens at a specific point. So the temperature does not change. That much is clear. So since the internal energy is actually dependent on the potential energy plus the kinetic energy, this is not changing. So internal energy entirely depends on the potential energy. Now we have to think about the potential energy. Now potential energy depends on the bonds of the solid atom. What is happening to the bonds of the atom or of the structure? So the relationship goes something like this. The potential energy is inversely proportional to the number of bonds or the strength of bonds. Now we understand that if it melts, it goes on from being a solid to a liquid. And liquid has less number of bonds, right? So since the number of bonds decrease, the potential energy increases. It's counterintuitive, but that is how physics, the concept goes, right? So that's why this answer is it increases, right? Okay, the next question is that he places a 300 gram of iron in boiling water until it reaches 100 degrees centigrade. So today iron is at 100 degrees centigrade. Removes the iron and then places it to 100 grams of water at 25, and after the mixture cools down, the thermal equilibrium establishes at 44 degrees centigrade. He says no energy is lost to the surrounding. Okay, good enough. Calculate the change in internal energy of the water as it warms up. So to calculate the change in energy, we'll have to use the formula as Q equals to mc delta T. Now, the mass of water is 100 grams, right? Do we need to convert grams into kilograms? No, because the specific heat capacity is given to us is in grams as well. So for 100 multiplied by 4.2 into the delta T, a change in temperature would be from 25 to 44. So this will be 44 minus 25, right? So the final answer comes out as 7980 joules, which will be rounded off to two significant figures as 8,000. Calculate specific heat capacity of the iron. So this is the energy that was brought in or was absorbed by water. You see, water was at 25, but today it is at 44. Which element heated it up? Which element or which substance was responsible for increasing the temperature from 25 to 44? It was the piece of iron which was at 100 degrees centigrade, which was replaced in the water. So the energy that it brought in was 8,000, right? So Q equals to mc delta T. Again, the energy brought into the system is 8,000. The mass of iron block is 300. Again, not converting this into kg, we should have, but since the specific heat capacity unit is in joules per gram, then we can leave this as it is. So C into delta T. Iron was at 100 degrees centigrade. When it achieved thermal equilibrium, it was at 44 degrees centigrade. So today, C comes out as 0.48 joules per gram degree centigrade. So this will be your answer, 0.48. Okay. You could have used 7980, you could have used 8,000. You will get the same answer up to two significant. There is a difference at the third decimal place. But when you convert this to two significant, this rounds off to 0.48. Question number 5, it says water waves generate transverse waves. Underline two other examples of transverse waves. So one of them is seismic S wave and the other one is X-ray. Now you might be confused that you may have skipped the seismic P and S waves in your books or probably in your notes. But I will remind you, I will bring back to you to the syllabus. You will see that this is in 3.1, that the candidates are supposed to know that the transverse waves are not only electromagnetic radiation, they're not only this, they're highlighted in blue, they're also going to be the seismic S waves, this one. This is also part of the transverse. Now you should remember them. These are one that cause the earthquake, responsible for them in earthquakes. And for longitudinal, apart from sound and ultrasound, P waves are also longitudinal in nature. So since it is already mentioned in the syllabus, that's where the examiner has brought the question to you. Okay. The next question is that a ripple tank is producing waves. The glass block is a bit higher. So if we were to visualize it in 3 dimensions, this is what it's going to look like. This is the ripple tank. This is the water. This is the bar that produces waves. And let's say this is the water level. Then this glass block, which is placed over here, is actually at a higher value. It's actually at a higher height, at a greater height than the water itself. So the water is not going to move above the glass of water. It's going to actually squeeze through this way. And the wave that is actually colliding with this plane is just going to get reflected back like this one. And you will see a partial diffraction at this corner and so forth. But that's a bit higher level physics. It goes up to A levels, but up to this point, we can see that the glass block will not be experiencing any waves. There will be no waves over here because the water level is lower and the glass is actually higher. So no deep to shallow, no shallow to deep, nothing like that. As he mentions this over here, that the depth of the water in the tank is less than the height of the glass block. So the glass block is higher. So the wooden bar moves up and down and produces a wave every 0.15 seconds to create the crest. Okay, so to create the crest, okay, fine. So crest to crest, it takes a time of 0.15 seconds, right? The speed of the water wave is 27 centimeter per second. So calculate the frequency. The frequency is equal to 1/t. So the time frame between 2 crests, 2 trough, or 1 complete wave. So this would be 1 divided by 0.15. This gives us 6.66 recurring decimal place. So this comes down as 6.7 hertz. The second part is calculate the wavelength. Okay, so wavelength, we will use V equals to F lambda. So speed is given as centimeters. We can see that the unit of wavelength is also centimeters. So we don't need to convert this into meters. This will be 27 equals to F 6.7 into lambda. So lambda comes out as 4 centimeters or 4.0 centimeters. This will be 4.0. He says that the wave diffracts at the right-hand edge of the glass block. We understand that. He says draw 2 crests after they pass the glass block to show the diffraction. Let's go to the diagram. We understand that there's going to be nothing over here. There is no shallow to deep or deep to shallow concept going to apply over here. There is no refraction primarily, but there needs to be a diffraction because it's passing through a narrow gap over here. So how do we go about this? Now, the area right in front of the edge, which is not encountering the edge, which is not in front of the gap, will carry on its life in straight lines. It will not be affected. And please make sure that you take a measurement, although it's mentioned not to scale, but we can follow the same scale, right? So if this, according to your rulers, comes out as 1.1 centimeters, then make sure that these are also at 1.1 centimeter. Follow the same scale. You can choose to draw them with a ruler. You can go about this just with the inspection of your eyes. It's up to you. But I would advise you to use a ruler. So the wavelengths should remain the same. Diffraction does not alter the wavelength. Since he's asking us about 2 crests, we can eliminate the third one, right? Only the wavelength that encounters the edge, which is this one, will undergo diffraction. So it should undergo the curving or the bending effect like this, but we can't change the wavelength. So when these remaining wavefronts are encountered by the edge, they're going to curve like this. They're going to curve like this. And if by chance we had drawn a third one, let's say you've ignored the instruction by the examiner, you draw a third crest, it will go something like this. And please make sure that by inspection by eye, these wavelengths should be exactly the same to these ones. They should not be changing, right? So the first crest and the second crest, we've drawn them successfully. Now let me show you an animation in which you can see this happening in real life. This is one of the animations from PHET Colorado, right? So let's see if we can see this over here. Now, first, let me show you where the crests are. So this is a crest, this is a crest, this is a crest, and this is the narrow edge where it passes through. Now notice that right in front of the edge, the place where there is no changing, where there's no bending, is exactly in front of the space itself. They are not bending, right? But when you encounter, for example, when you encounter this edge, that is this one, right? So they start bending like this. They're bending like this. Let me choose a different color for this. They're bending like this, so on and so forth, as if you can see, like this, right? So I'm going to remove all of this, and I'm going to allow you to visualize this, at least in terms of the animation. So let's play this animation and see how it's going to go. So you can see that the wavefront in front of the space does not get bent, but the one that encounters the edge is curving in circular direction, exactly like we have drawn over here, right? So I hope that this is clear. Okay, describe how the wave with a smaller wavelength is made with a wooden bar. So if you want to reduce the wavelength, you reduce the speed of the bar. If it moves very frequently, right, so the wavelength reduces. He wants you to, the wavelength is made with a smaller, right? So we reduce the frequency of the bar moving up and down, okay, right. So smaller wavelength means that if this is a wavelength from crest to crest, we want to reduce its wavelength like this one. So you reduce the frequency, you reduce the speed. Next is describe how the decrease in wavelength affects the diffraction. So again, this is from diffraction, that the extent of diffraction is dependent on the wavelength. If you decrease the wavelength, the diffraction effect also decreases, or the bending decreases or reduces. Question number 6 is a simple DC circuit. We have 12 volts of battery. We have ammeter 1, ammeter 3, and ammeter 2. Luckily, all of these ammeters will produce the same reading because it's a series circuit. And then we have a voltmeter 1 in parallel to the bulb, and voltmeter 2 in parallel to the resistor. The ammeter A1 reads 0.25. This one reads 0.25 amperes. And determine the reading on the other meters. So A2 and A3. The current in series circuit remains the same, and voltmeters do not receive any amount of current because they have high resistance since they're connected in parallel. So A2 will produce the same reading, and A3 will also produce the same reading, which is why the answers to this question will be 0.25, 0.25, exactly the same. Reading on V2. This is interesting. Now he says that the reading on V1 is 3 volts. Okay, fine. We understand that for series circuit, the current remains the same throughout the circuit, but the voltage divides because voltage is energy. So 3 volts of energy has been taken by the bulb out of the 12 total. So if 3 volt has been taken by the bulb, the remaining goes to the resistor, which is going to be 9 volts. A very easy question. So 9 plus 3 is 12. Okay. So this comes down to 9.0 volts. He says calculate the resistance R of the resistor. Resistor R. Okay. So the resistor R is receiving 9 volts at a current of 0.25. So simply apply V equals to IR. 9 volts received at a current of 0.25. The resistance R comes out as 36 ohms. So this will be 36. Very straightforward. He says that, now again, Ohm's law, we have memorized this, that the current produced in the component is proportional to the potential difference. So the potential difference is proportional to current, but as long as the resistance of the component remains constant. Now we can't say the resistance directly because at the time it was not known. They were just discovering Ohm's law. So we understand that the resistance alone is dependent on the temperature, is affected by temperature. So instead of saying that resistance should remain constant, we say indirectly that the temperature remains constant. The next question is about the filament lamp, which is connected over here. This is the lamp. This is the bulb that he's talking about in the same circuit. He says this is what it looks like. Okay, fine. So he says that the battery in figure 6.1 is changed by a different battery, a new battery that has a different EMF. Now he doesn't tell you whether the EMF is high or the EMF is low. The voltage of the lamp increases to 6 volts. Now previously it was 3 volts, today it is 6 volts. Let's make the circuit again. So the EMF is unknown, but the bulb today consumes 6 volts. We don't know what is going to happen to the resistor. We don't know what its information is, but we know that the resistance of the resistor remains fixed, right? So use the data from the graph to determine the EMF of the second battery. Show you're working. So we go to the graph and we see that at 6 volts, the current in the circuit is 0.35, right? Now you have to show this to the examiner. What you can do is use a dotted line with a lead pencil and a ruler, draw a straight line and show to the examiner that you're reading this value from the graph, and mention to the examiner that from the graph, and which graph are you talking about? 6.2. From graph in figure 6.2 at V equals to 6 volts, the current has been found to be 0.35 amperes, right? So the current in the series combination is still 0.35, or has increased from 0.25 to 0.35. So definitely if the current has increased, this battery must have been greater than 12 volts. Now let's see how to find it. Now we understand that the resistance of the resistor today must still be 36 ohms, right? But we don't know the resistance of the bulb itself. We can find it by using V equals to IR. So 6 volts equal to I, which is today 0.35 into R. So R is equal to 6 divided by 0.35 is 17 ohms, 17.1 ohms. Now this is 17.1, this is 36. So the total resistance, or RT, becomes 17.1 plus 36 as 53.1 ohms. Now for the total circuit, again using V equals to IR, so we don't know the EMF, but we know that the circuit is receiving a current of 0.35 and the resistance, or the current total resistance it has to push through, is 53.1. So 53.1 multiplied by 0.35 leads to 18.5 or 18.6. So this is 18.6 volts, which up to two significant figures comes down to 19 volts. You could have used the potential difference formula or the potential divider formula. How you could have done that is simply find out the resistance of 17.1. Then you understand that the voltage of the unknown component is equal to the resistance of the unknown component, X. Vx equals to Rx divided by total resistance multiplied by the EMF of the battery. So you could have selected this component, right? So Vx would be 6 equals to 17.1 divided by 53.1. The total is multiplied by EMF. When you solve this equation, you will ultimately find the same answer again. So there were two ways to solve this question. Question number 7. Ultraviolet radiation is one of the components. Okay, fine. State two of the components that have a smaller wavelength. So there are gamma and X-ray. So gamma, X-ray, ultraviolet, and then so on up to radio. So he's asking for smaller wavelengths. So these are X-ray and gamma. State one useful application of ultraviolet radiation is it kills bacteria from medical equipment. It cures dental fillings and checks for banknotes. You can also refer to the marking scheme. There are many more answers written over there, which you can use to memorize all of them. It's up to you. He says state exposure to the ultraviolet radiation from the sun damages the eyes. State one type of damage to the eye specifically by the ultraviolet radiation. So it can cause the skin cancer, or it can ultimately destroy the retina or the lens of your eyes. Shows a light ray passing through the semicircular glass block, and this is a common question. We understand this. He says name the angle 40 degrees. So this is actually an angle of incidence in the dense medium, which causes an angle of 90 degrees on the rayed medium. Then this angle of incidence is named as the critical angle, which is mentioned over here. So calculate the refractive index. So we understand the refractive index is actually equal to 1 over sine of C, the critical angle. So n equals to 1 over sine of 40. When you calculate this, the n comes out as 1.6 up to two significant figures. Question number 8 is from transformers. So he says that the primary coil and we have a secondary coil. We can guess just by looking at this is going to be a step-down transformer, although he mentions that, but we can guess it ourselves as well, because the number of turns on the primary are much greater than the number of turns on the secondary. So definitely the voltage is being reduced on the output. So it's a step-down transformer. State the material. Again, a question from memory. The core is made out of soft iron or iron, because we want to magnetize and demagnetize it very quickly so that changing magnetic field can reach the secondary coil. He says a current, explain how the alternating current is produced. Again, this is a repeated question in terms of how voltage is produced on the secondary coil. Alternating current, let me explain this to you and then you can read the answer. Alternating current in the input side causes the magnetic domains in the core to change their location as well. So this is what the domains may look like because of the positive cycle. Let's say this is the positive cycle. When the negative cycle arrives due to the AC current, these domains change their direction in the reverse order, like this. Now, when you complete this loop, for example, through the whole core, like this, right? We can observe that the green direction is downwards and the blue direction is the opposite one, right? Now, when the secondary coil experiences this changing magnetic field, it experiences induced EMF, which is Faraday's law, right? And the voltage experienced by the secondary coil is less because there are less number of coils. If the coils are less, it produces less voltage because there is less cutting of the magnetic flux or the magnetic field produced by the magnetic domains. So this is what is explained in the question or in the answer, that the alternating current in the primary coil causes the changing magnetic field in the core, in the iron core, where the magnetic domains or these arrows are drawn. This produces a changing magnetic field on the secondary coil over here. It experiences sometimes an upwards magnetic field and sometimes a downwards magnetic field due to the AC supply. This changing magnetic field cutting the secondary coil, cutting is mandatory for Faraday's law implementation or Faraday's law understanding. Cuts the secondary coil, which causes the induced EMF on the secondary coil. This is a repeated question. You can memorize the answer. It's up to you. He says, find the number of turns for the secondary coil if you want to reduce the voltage to 5 volts if the primary has 4600 turns. The formula is very simple. The number of secondary turns divided by number of primary turns equal to voltage of secondary divided by voltage of primary. So replacing the values, the primary number of turns are 4600. The secondary voltage is 5 volts as mentioned. The primary voltage is 230 taken from the source. So taking 4600 over there, being multiplied, you come down to the number of secondary turns as 100 turns. So the primary may have 4600 turns and the secondary has 100 turns. Then if you supply 230 volts on the input, this side will give you 5 volts. So basically you can say that this question is for mobile phone chargers. That is one transformer that they have inside them that takes 230 from the source, from your electric supply company, and makes it down or brings it down to 5 volts, which is safe for the mobile phone battery charging. So the number of turns that are going to achieve this is going to be 100 on the secondary side. It says state one change that can be for the transformer 8.1, so it can be used as a step-up transformer. No problem. If you're supplying input from the higher number of turns from this side, then swap this side and provide input from this side. If you provide input from this side, the number of turns naturally on this side are less than the number of turns on the output side or on the other side if you swap the sides. Or what you can do is increase the number of turns on the secondary side much greater than 4600, then it will again become a step-up transformer, right? Okay, so either swap the sides or increase the number of turns, okay? All right, a secondary radioactive source emits alpha, beta, and gamma radiation. State the type of radiation produces strongest. So alpha produces strongest ionization. That's why if you're standing very close to it, the DNA damage is almost certain. State which type of radiation is deflected most. In the beta is deflected most because it has less mass in comparison to alpha. 9.1 shows GM tube. He says it is placed 10 centimeters. Now he's very, very clever about this 10 centimeter. Be careful about this. You see, alpha particles have a range less than 10 centimeters. So if the source was emitting alpha, it would not have been detected because alpha usually don't travel up to 10 centimeters. They release, or you can say they collide with the air particles, and their energy gets eliminated. They get slowed down. Okay, so the next question is, he says that now we place a 5 millimeter thick sheet and the radiation reduces from 800 to 200. Now we understand that it says that the background radiation has been corrected. If the background radiation has been corrected for, then it means that if the radiation definitely comes down to 0, if there is no radiation, if you place a lead sheet at the center, this will come down to 0. So for this question, for the sake of this question, we don't have to think about the background radiation because it has been corrected for, which means that if it hadn't been corrected for, then this would have been reading 820 or 830 because we know that the background radiation from memory is generally 20 to 30, right? Not a fixed value, it depends on the area where you're closer to the radiation source or not. So this is just a commentary before starting the question. So explain how the readings show that it emits beta and gamma. Notice that he's not asking you about the justification of alpha, right? So we don't need to waste our writing space for alpha. If you do end up having more space, then you can justify for alpha, but the primary answer or concern should be beta and gamma. So how do you know that this does provide beta and gamma? You see, we can argue from 800 to 200, which means, and even with the presence of the metal sheet, it means that beta generally is stopped by the metal sheet. So this is not showing beta, this is showing gamma only, which means gamma is definitely present, right? So, and over here with 800, if you remove the lead sheet, it means that beta and gamma both are present, because generally up to 10 centimeters, alpha cannot travel up to. So it contains beta because the value reduces from 800 to 200, because after placing the sheet, all of the beta would have been absorbed or stopped. And if it still does not come down to zero, which means gamma is also present. So if, let's say, beta was not present, then placing this sheet would not affect the value. It would still be 800. It would still be 800. But since placing the sheet reduces the value, it means that beta is there. So absorbed by the sheet, container still maintains reading of 200, which shows that the gamma is still present. Now, gamma can pass through metal sheet, can pass through paper, it can pass through anything, everything almost, except it reduces its concentration or its effect when you place a thick lead sheet. And over here, you can say that alpha is not detectable or is not a part of the question because of the 10 centimeter range. It's up to you. If you are not left with the writing space, then you should be good enough with the justification of beta and gamma. State by the readings cannot be used to show the source emits alpha particle. So alpha has low range and it is stopped by air, hence it does not reach the GM tube. Tube is to detect successfully, giving reading. Why? Because the range of the alpha particle is too low. Why? Because it is stopped by air, right? And again, exploring why, we understand that the particle size is too big, right? It collides, or its chances of collision with the air particle is higher. Describe one way the radioactive source still moved safely in the laboratory. So using tongs, stored inside a box lined with thick lead sheets, or wear a hazmat suit which is lined with lead. Or reduce exposure time and work with them as least as possible. The astronomical distance I measure in light years. What is light year? So a distance traveled by light year in 1 year in a vacuum, or the speed it has in vacuum. The sun is one Milky Star away, is a part of Milky Way. Stated approximate diameter of the Milky Way, this is 100 to 150 million light years. Again, part of memory. This life cycle I've explained to students many times, that just remember this, just memorize this. No questions are, memorize it. And you can see that in the question, he's asking you about the life cycle. He could have mentioned, he could have missed all the other details as well, but he has not. He's given us a starting point. So since is the star much larger than our sun, it meets a fate of becoming a nebula or a neutron star at the end of its life cycle, right? Or a black hole. So the next part is state the change where the heavy elements are formed. Again, called from memory, it's a supernova stage, where the heavy elements are formed, for example, because we understand that stars are burning hydrogen to become helium, right? So in the universe, how do we get uranium? How do we get lead? How do we get iron? How do we get the elements that make us, that make our bodies? Those elements actually come from the supernova stage, when it compresses and compresses and compresses more and more, causing more fusions. So helium combines together under high temperature and pressure to become other elements of the periodic table. So current scientific understanding is that the universe began its journey 14 billion years ago. It's 13.8 to be exact, but for the sake of example, it's 14 ago in an event known as Big Bang. So explain one observation, right, in which the theory is supported, right? So we have the redshift theory coming from Doppler effect, which says that the wavelength perceived, or the perceived wavelength of light actually increases. So for example, if you're observing the sunlight of your own sun that is a yellowish, that has a yellowish tint, let's say it is 600 nanometers, for the sake of example, right? If you observe the same wavelength of a star that is much away from you at night, right, you see in the laboratory that the wavelength is somewhat, let's say, 650 or sometimes greater than 700, which is not even visible to us. Why is that so? All of the galaxies in the universe have the same star, have the same sun, have the same process of making a star. They're burning hydrogen to make helium. So they all should be releasing the same amount of wavelength, the same visible spectrum wavelength that we are able to see. But if a distant star is to my perspective, is looking to me like a red color, is looking to my eyes that it is moving towards closer to a wavelength which is red in nature. 700 is actually red color, right? Nanometers. It means that the wavelength are shifting. This is the phenomenon that is called as redshift, coming from Doppler effect, that the sources that are away from you are moving away from you, their frequency decreases and wavelength increases. You can explore more about the Doppler effect and its respective effect on my separate video on the Big Bang theory and Big Bang explanation of the space physics on my channel, right? So the fixed answer would be that the galaxies furthest away, the galaxies that are further away from us, represent a greater change in wavelength. Their redshift is higher, representing that the galaxies are moving away from each other. Now, we argue that if they are moving away from each other today, there must have been a time previously, there must have been a time, if we go back in time, previously, in the past, there must have been a time when they were all together. If today they're moving away, there must have been a time when they were together as one big lump, right? So this means that the universe must have been in a dense small state at its very beginning of life, which means that Big Bang theory is true. This Big Bang has happened, and this has caused the universe to come into existence as we see it today.